Assalamualaikum and a very good day to everyone. Today our group will present the topic titled HTML Interactive Electrostatic Application using AI tool that we create to calculate the electric field on the perpendicular bisector. Before I start, let me introduce my group member first. We are group 4, consists of Muhammad Fawaz bin Muhammad Fauzi, Nur Akida Yuni binti Zulkifli, Ani Sofia Nurmai Sarah binti Muhammad Zamri, Bao Shuyen, and myself, Nur Ain binti Muhammad Zulkifli. To begin, let's recall the meaning of electrostatic. Electrostatic is the study of electric charge at rest and how they interact with one another. When objects become charged, whether it is positive or negative, they will exert force on each other. For example, two like charge will repel on each other and two opposite charge will attract to each other. This interaction is described by Coulomb's law, which is E equals to kq over r squared. And even when the charges are not moving, they still influence the space around them by creating an electric field. Electric field is defined as force per unit test charge. The formula for electric field is E equals to F over Q, or E equals to 1 over 4 pi E naught multiplied by Q over r squared. This means if we place a small positive charge in a region near another charge, it will experience a force that tells us the electric field at that point. For positive charge, the direction of the field line is always pointing outward, while for the negative charge, the direction of the field line is always pointing inward. Now we are moving to our main topic, which is to calculate the electric field on the perpendicular bisector. Here we have line of the rod L, density of charge lambda, total charge Q, and distance of point P from origin Y. The formula to calculate the electric field is E equals to 1 over 4 pi E naught multiplied by Q over r squared. But instead of using manual calculation to calculate the electric field, our group already created a tool for continuous charge distribution.
In this part, we're going to dive into the prompt for creating the HTML application to calculate the electric field E created by uniformly charged rod. We use Gemini to execute the prompt. So the scenario is specific. The rod lies on the x-axis, and our point of interest P is located on the y-axis at a perpendicular distance y, right above the rod's midpoint. So let's look at our prompt here. This sentence instructs to build a web page that models a rod lying along the x-axis and computes the electric field at point P. Our task requires three key parameters. We need the rod length L, the total charge Q, and crucially the constant charge density lambda. The UI should expose these three parameters, that is L, lambda, and Q. So these inputs define our entire system. This sentence intends to compute the different parameters using the attached formula derived from integration. This ensures academic correctness of the calculated parameters. Using the analytic formula is faster and more exact. So this is the formula used to calculate the magnitude of electric field at point P. This sentence intends to include the provided image in the interface. The sentence here gives the user immediate feedback when the parameters are changed, such as numerical output, visualization, sliders, and live updates. This means that as you adjust the value of lambda and or Q, the result dynamically updates in real time. The interactive interface can improve intuition about how geometry and charge affect the field. The sentence instructs to include a concise theoretical explanation of the physics, which can be what a continuous distribution is and how geometry influences the result. It will allow the application to be not only as a calculator, but also educational. So we have described the prompt used to generate the HTML application. So now let's see how the generated HTML application looks like. So this is the code of the generated HTML application, and this is the preview of the HTML application interface. We can see that it contains all the requested features as written in the prompt.
This is our electric field calculator. The title clearly shows what the app is used for. Here on the left, users can set the rod length and the distance to the point P using the sliders. They can also choose to define the total charge Q or the charge density lambda. On the right, we choose a visual diagram. The orange line is the rod, and the right arrow shows the electric field at point P. The diagram updates when input charge. Okay. The physics explanation below describes the symmetry argument and shows the formula we use for the calculation. Is the formula. And at the bottom, we display the electric field results at point P in scientific notation. So the layout is quite simple. Input on the left.
Okay, so hi everyone. Now I'm going to test the application whether it is accurate with physical calculation or not. So here we have the electric field calculator application. So to compute the electric field, I will put the value of rod length as 5 meters and the distance to P as 2 meters. And the total charge I will put as 2 coulomb, and we got the result at point P, which is 2.8073 times 10 to the power of positive 9. And this is the visual representation for the value above. To prove whether the application is accurate, I'm going to compute all the values into the calculator using this equation, E1. So the calculator gave us the answer as 2.807 times 10 to the power of positive 9. This has the same answer as the application. So to prove more accuracy, I will compute another values, which is 7 meters for rod length and 3 meters for distance. And the total charge is 4. And I will also compute it into the calculator. So the calculator gave us the answer as 2.599 times 10 to the power of positive 9. This is the same as the result at the application. What if the value of y is much larger than L? So based on the key insight in this application, as the distance y become much larger than L, the formula will approximate to Coulomb's law. To prove this, I will compute the value of y is much larger than L. We put y as 300. So we got the answer as 3.9943 times 10 to the power of positive 5. And I will compute the Coulomb's law formula into the calculator. So by using the Coulomb's law formula, we got the answer as 4 times 10 to the power of 5. Almost the same answer as the result in the application, which proves this statement.
Summary: from the simulation, we observed the accuracy of physical calculation with the physics application. We understood how the electric field behaves on the perpendicular bisector, especially how the symmetry causes some field component to cancel out while the others is adding up. We also learned how to apply this physics equation into code by calculating electric field vectors, adding them, and visualizing the results in applications. This helps us to see how the mathematical concept turn into the real simulation. In conclusion, the electric field on the perpendicular bisector demonstrates how the symmetry simplifies electric field calculations. Understanding this relationship is important because it shows how electric fields behave in a real physical system and help us to build a basis for analyzing more complex charge arrangement. We were able to create a simple simulation that shows the direction and magnitude of the electric field on the perpendicular bisectors. In the future, we can use the coding logic to build more complex physics simulators and help us to create other physical systems in the future projects, such as electric fields from the multiple charge, dipoles or continuous charge distributions. This basis also help us to create interactive tools for learning physics and analyzing a real-world electric system.